My talk is on side effects in Samos Island. I'm talking on behalf of a group of Greek scientists working in different parts of the country, as well as in the UK and the US. This is a map of Samos Island. Of interest for us is this area here of Vathi, which is the capital of the island. It's approximately 10 kilometers from the rupture. Geologically speaking, the bedrock of the area are metamorphic rocks, mostly marbles and schists. Other rock formations of interest are this orange-like limestone, marly limestone, and obviously some quaternary soil deposits near the seaside of Vathi. Here's the Google image of the area of Vathi. Of interest to us is Vathi, which is the seaside part, and this area here, which is called Ano Vathi, Upper Vathi, that means. Here's an image from the sea, this seaside town of Vathi, and here up on the hill is Ano Vathi. I will tell you beforehand that Vathi itself did not suffer significant damage. Oppositely, Ano Vathi did. Just a sneak preview of damaged buildings in Ano Vathi. You can see all these red circles here are damaged buildings. And if you do a close-up, you can see, for example, the damaged dome of the church. Now, for us, this was the inspiration. But we are geotechnical engineers, so let's look at geotechnical conditions in Vathi, in the seaside town. The red pins are the two recording sites of Ilgac here and Noah here. In geological map, all this area here is alluvium. We found two boreholes. For example, this one to the west gives you soils up until 15 meters at least, with the average SPT of 25. Going towards the west, towards the east, I'm sorry, the second borehole, again, we see soils up to at least 15 meters, but an SPT blow count, which is much higher. So we have an increasing stiffness going towards the east, whereas the Noah site seems to lie on outcropping marbles. Now, we as a team, we perform geophysical measurements at these recording sites. A team from the University of Patras, headed by Professor Pelekis, did the MASW measurements and picked up VS30 values of 550 at Ilgac and 840 at Noah. So there is some agreement between geology, geotechnics, and geophysical measurements for the two recording sites. That said, let's look at time histories in the two sites. On the left, Ilgac, on the right, the Noah. I'm giving you time histories only in the southwest northeast direction, which was the most intense motion, which is transversely to the radius coming from the hypocenter towards the Vathi area. You can see here the two recordings. Up are the accelerations, on the bottom, the velocities. Pretty in long durations, 7 and longer in the softer site, modest PGAs up to 0.23 G and 22 centimeters per second. These are time histories of acceleration and velocity, but as engineers, we're mostly interested in elastic response spectra. Blue curves are the southwest northeast in both locations. To the left, the Ilgac, the softer site. To the right, the Noah, the more intense, the more rocky site. The red curves are the other horizontal recording. The green are the vertical recordings. And with black are the EC8 design spectra for these two locations, which are different because this is ground category A, this is ground category B. You can see clearly that there is more intense motions at the Ilgac recording. You can also see that these both recordings share also a common predominant period, which is approximately between 0.4 and 0.6 seconds. Now, Having that in mind, we may consider an approximation that the NOAA recording is a rock site and the Ilgac is a stiff soil site. So we can take the standard spectral ratio, Ilgac divided by NOAA. This will give you an estimate of 1D amplification, and clearly there is 1D amplification in the town of Vathie. You can see the PGA of around 40%, but on average, I would say that the 30%, at least the 30% 1D amplification is appearing for the structural periods of interest. However, this area did not suffer significant damage, so let's shift to the second area of Anovathie. Now, Anovathie is here on the hilly side. Interestingly, it lies exactly on top of the Marley limestone. So in order to understand geography and topography, and as well as geology, we will take a northwest-southeast cross-section. This is it in a distorted scale, mind you, which gives you a slope of approximately 170 meters, but a mild inclination of 13 degrees. Anovathie itself is here on the thick green line. So it lies exactly on the Marley limestone, which overlies the Marley bedrock of, the marble bedrock of the area. Now, what would EC8 tell you about this type of topography? It would tell you that because the inclination is less than 15 degrees, there are no topography effects. However, if we disregard that and we consider that Anovathie is at the mid-height of the slope, so we have an amplification of 1 here, amplification of 1.2 here, we can have an average of 1.10 amplification of the horizontal motion according to the EC8. If we look at other published results, which gives you approximate estimates of topography effects, they would agree. 1.08 for the horizontal component, but also something not recorded by any code, that you have parasitic vertical accelerations, approximately 14 to 20% of the horizontal motion, which are long period motions and appear only for the low period components of the motion. This is what we expect to have occurred according to this northwest-southeast cross-section. If we take the other cross-section, southwest to northeast, this is the image that you would see. You would see a valley-shaped formation. Again, Anovathie is here with a thick green line, which lies on the Marley limestone overlying the bedrock, which is mostly marbles in this area. Now, this type of valley effects do not exist according to codes. However, if you look at published literature, you can pick up some estimates of what might have happened here, and you can pick up a value of 35% amplification, up to 35% application only for the low period components. Working on this, looking also at other published studies, we can say that this 35% amplification should be expected at least in the southwest side of Anovathie, because here the bedrock inclination is more intense, and you also have this outcropping bedrock, which also adds to what occurred in this area. However, in the northeast side, things should be milder, less intense, and a value of 16% is what we expect to have happened. Now, the interesting thing here is essentially that we have a coupling of topography effects in the northwest southeast and valley effects in the southwest northeast direction. So we have to combine them. We have to combine them to see the total image. And this leads us to a 45% amplification in the southwest side and a 25% amplification in the northeast side. Not to forget the parasitic vertical acceleration, which must have appeared also throughout Anovathie. To conclude, Vathie, the capital of, has 2 recordings which gave us modest PGAs and modest PGVs, given the rupture and the epicentral distance of the earthquake. However, they are long period recordings and a long duration recordings which are compatible with the fault rupture size. Now, we may consider the NOAA recording as being recorded on a rock site and the Ilgac on a stiff soil site, which gives us a very interesting case study, I would say, of 1D soil amplification of 30% on average between the two, because these were approximately 230 meters apart. However, no significant damage at Vathi. That's not the case in Nanovathi, where we have what we can say a 3D coupled valley and topography effects that led to a 25 to 45% amplification of the horizontal accelerations, especially for low periods, which are of interest here because we have low-rise buildings, and the apparition of long period parasitic vertical accelerations. Now, important thing here is to underline the long period. That is not what the actual earthquake vertical acceleration had, that it was high frequency. Finally, more research is needed on this side. Of importance is to correlate what we expect to have the spatial variability of the motion that we estimate, correlated with the observed structural damage that you will hear further in the evening when we talk about chapter 7. With this, I would like to thank all these fine individuals and researchers in their help in our work. Thank you very much.
Thanks, Achilles, for the very interesting information you presented. I don't see questions for the time being. Before passing the torch to Kemal to continue, I would like to make a point that this is probably a very old settlement, very Nanovathi, much older than the one close to the shoreline, for the very simple reason that out of fear of pirates, people in the Aegean area before approximately 1850 tended to build their houses uphill at as high as possible, and this is very compatible with this picture. So we might also provide a comment here that many of these buildings must date as early as the 18th century. Having said that, I would like to thank you again, Achilles, and pass the torch to Kemal. Kemal, the floor is yours.
George, thank you so much. Thank you for this wonderful presentation. I feel like the flow of the presentations will be wonderfully arranged, because we will talk about something that is complementary. I have shared my slide, and then I will try my best to basically keep the time limit of 20 minutes. What we're going to do today is, in that 20 minutes, we'll talk about the site effects from the Anatolian site. So in this presentation, we will simply talk about Izmir Bay, the geotechnical setting of Izmir Bay, and then we will compare available rock and soil motions, and then we will discuss what could be the effect of source and path effects on this available records. And to be able to do that, we have performed some preliminary site response analysis, which we will share the results with you all. And then we will try to understand the effect of the site-related issues on the observed structural damage, mostly pronounced in Bayraklı, and then say a few words about code-based amplifications. As you see here, we have a long list of contributors because this effort requires collaborative input. We have some geophysicists, geotechnical engineers, geological engineers, professors, master students, PhD students, professionals. So I truly appreciate all their contributions. To be able to understand this issue, first, we need to understand what has happened in Izmir. So I would like to kindly ask Professor Selim Altun to give us an overview of damage observed in Izmir.
Yeah. Thank you, Professor Cetin. First of all, I would like to thank to both sides and colleagues to organize such a webinar even during the difficult pandemic days. I'm also very pleased to be attending and participant in this collaborative organization. We know that a big earthquake struck offshore about 13 kilometers to the north of the Samos Island and to about 15 kilometers south of the Turkish coast in the eastern Aegean Sea. Although the many buildings were damaged or collapsed and 2 lives were lost as a result of the earthquake in Karlovas Samos Island, but the most damage occurs in the city of Izmir, located about 65 kilometers to the north of the epicenter. And this effect results many lives lost, and at least 7 and 20-story buildings were strongly affected. But high-rise buildings is still standings. To understand this, of course, we should look at the underground soil conditions. And in that meaning, we can transfer the words to the Professor Kincal, who is the professor in the geology department at 9 Eylül University. The word to yours, Professor Kincal.
Thank you very much, Professor Altun. Dear colleagues, I would like to mention about geological setting of the Izmir city and its surroundings. Izmir is located in the west of Turkey. Geological units are Upper Cretaceous, Paleocene age Borneo melange rocks, Neogen age sedimentary and volcanic rocks. Alluvium discordantly overlie existing geological units. Next slide, please. Aegean region has high earthquake potential due to its active horse graben structure. Aegean region was subjected to many earthquakes in the past. In and around the Izmir, blocks bounded by deep slip normal faults trending in east-west direction. Izmir fault in the south and Karşıyaka fault in the north. These structures are typical for the western Anatolia. Next slide, please. Alluvial plains exist around Izmir Bay, which was developed on the same terrestrial fields, but their geomorphological aspects are different. We see typical borehole logs from Gümüldür, Sığırcık, Seferihisar, Mavişehir, Bayraklı, Karşıyaka, Semikler districts. The thickness of the alluvium is changing. The maximum thickness of the alluvium is recorded in the locations such as Karşıyaka, Bayraklı, and Bornova, up to 400 meters. Thank you, Professor Kemal Önder Cetin.
Thank you so much. That was a brief overview. Now I would like to again ask you to share available recordings from Izmir Bay. Would you please summarize that, Professor Altun and Professor Sezer, very quickly, please?
Thank you. We know that many stations located in Izmir to record the earthquakes. Some of them is located in soil area, but some of them is outcrop. And Professor Sezer briefly discussed these differences, please.
Thank you very much, Professor Cetin and Professor Altun. So, as mentioned in the previous section, Turkish strong ground motion network in the vicinity of Izmir city is well established, and the 8 accelerometers are founded on soil or alluvial layers, and 5 are established on rocks. Next slide, please. As you can see, from the elastic response spectra of the strong ground motions on soil and rock sites on Izmir Bay, we can notice different spectral acceleration period relationships, which are established on soil and rocks. Deviation from mean is greater in soil sites in comparison with that on rock. As expected, the responses obtained on soil and rock are significantly different from each other, which is underlying an amplification issue here. Next slide, please. Paying attention to the recorded strong ground motions, it should be emphasized that the response somehow surpasses design basis, which is 475-year return period and 72-year return period response spectra, and the behavior between 0.7, maybe 0.5 and 1.6 seconds are very interesting. Thank you very much, Professor Cetin.
As very well explained by Professor Altun and Professor Sezer, basically this event produced a significantly different response on a rock and a soil site. And also the event itself is below 475-year design basis event. It is more of a 72-year return period event. To be able to understand the long period amplifications, the first hypothesis, the question to check is this because of the source and path effects? And to be able to answer that question, what we did is we compared available recordings closer to the fault and see the response there. This is a motion from Samos Island. As you see that in the period range of 0.5 to 1.5 seconds, compared to ground motion prediction equations, we have a significantly pronounced, relatively long period energy. So remember, this is the period of the buildings that were damaged in Bayraklı. So the same pattern also continues if we move along on the Anatolian side. Now we're looking at another ground motion station. These are rock stations. As you can see that on the VS30 values are relatively large. And we have an unusual, relatively long period energy at this motions. So the first part of the story, that we started with a very rich, long period rock motion, which arrives to Bayraklı and see, or İzmir Bay, and see how İzmir Bay site conditions affect that long period rich energy. And for that, I would like to invite Makbule Ilgac to basically discuss site response assessment results that are performed on rock motions. Makbule?
Thank you, Professor. Thank you. In this part of this presentation, let's focus on the İzmir Bay area rock ground motion sites. There are 14 stations in the İzmir Bay area, and 5 of them that I have marked here with the blue circles are located on strong rock sites. As an example to the surface recording of rock site, this is number 3506. The upper shear velocity, 30-meter shear velocity for this station is 771 meters per second. And in the map, you can see that this station is located in the south part of the İzmir Bay area. We have examined the data. We have looked at the acceleration time histories, velocity time histories, displacement time histories, Fourier amplitude spectrum. We take a look at the response spectra for all of the rock station, and we have compared it with the ground motion prediction equations. So if we draw all of them together, the black line represents the mean of the rock surface recordings, and the red line represents the predicted value of the GMPs. And here you can see the before mentioned high amplitude energies in the relatively longer period range. So we were curious about also the seismic bedrock level ground motions. So we have decided to perform some deconvolution analysis. So deconvolution analysis are basically a backward site response analysis where you inputting the surface ground motions and propagate it downwards of this 1D soil column. We are performing equivalent linear analysis, and the black line and the red line on these plots represents the surface recording, and the dashed lines here represents the within rock motions at 1.5 kilometer depth, where the shear velocity reaches 3,000 meters per second. And if we draw all the 5 stations within motions, and this is how it looks like, and the black line represents the average of these rock motion within rock motions, and still we see an expected high amplitude energies.
Makbule, you did an amazing job. Time is limited. I know that you're rushing. Thank you so much. This similar exercise was also performed on soil sites. Gizem Can, would you please tell us what we did with the soil station recordings?
Good afternoon to you all. This is Gizemcan from Middle East Technical University. Previously, Ms. Ilgac explained to you what is the data coming from the rock sites. And this map shows the rock sites actually. And on the next slide, on the map, you will see the soil site stations. Their VS30 values are in between 150 to 400 meters per second and around the Bay Area. Before doing any further analysis, we examined the surface recording for acceleration, velocity, and displacement, and we have compared their recordings with the available GMP results, available global GMP results. Here, if you see the GMP result coming from the Abrams and Silva 2014 model, we have a richness in the higher period ranges coming from the record itself, but this behavior could not be captured in the GMP results. And here we have studied for all the sites, and you see the results coming from all of it. And when we plot again, we did in the rock stations, their mean expectations and the mean results coming from the records, if we compare with the GMP, in the average, we can say that ground motion prediction models made the good work here. And also we did the deconvolution analysis again for the soil sites. For the upper 30 meters, we used the data from the AFAT ground motion database, and then we tailored this shear wave velocity to the available shear wave velocity results coming from the literature, and then we deconvolved the surface ground motion up to a bedrock level until 150 meters, and then we obtained a rock within motion for all the records for the Bay Area. Here you see for the results for the different soil sites.
When we did that, also, Selim Hocam, these are the deconvolved values. Would you please tell us, because look at it, these are the motions. They're in conformance except one station, which is the Konak station. I would like to kindly get your opinion why this Konak station is not acting consistently with the other stations.
Yeah, thank you. One of the strong ground motion stations is located in Konak region. If we analyze the records from the station record, some anomalies were realized, Professor Cetin mentioned. And Professor Sezer will try to explain the reason of this anomaly. Please, word of yours.
Thank you very much, Professor Altun. Talking about the anomaly here, 3518 Konak station may have provided an unexpected response, which is probably affected from its location. This station is located above the corner of an underground park in Izmir city center, which is known as Kültür Park. So this probably affected what we deduced from here, and we can evaluate the situation under these circumstances.
Thank you so much. A quick summary, we have done deconvolution studies by using rock and soil motions for Izmir Bay. Remember, it is about basically 70 kilometers away from the source. And then you see at 1500 meter depth. So this is an unusual exercise. You see that soil and rock within motions are very similar. Let's compare them by putting on top of each other. This is as good as it gets. So we are very convinced with the profiles that we use and with the methodology with which we use to basically deconvolve the available records. So we have good understanding about what happens at Izmir Bay. After having done that, what we did is basically we performed some site response analysis, and we tried to see if we can mimic the available recordings through use of rock station motions, outcropping, and then we deconvolve them to 1500 meter, and we apply it to the profiles that we developed, which extend all the way to 1500 meters, and we compare the outcropping motions basically with the recordings. That is the intention, and see like if we were doing a good job. When we did that, what we saw that, look at it, those red dots are the dots showing damaged buildings. What we saw simply is that the rock motion was extremely rich with long period energy. This is something unusual. We don't expect that. And that is beyond our ground motion prediction expectations or predictions. And then that rich energy was amplified by deep, long period alluvial sites. And then they basically, as you see that the amplification factors at certain periods may even reach up to a factor of 16. By the way, please be careful. This amplification ratio can be defined in multiple ways. Plus, this amplified motion was going into resonance with 7 to 9 story residential buildings, which happen to have the same period falling in that range. So we have, I would call it, double amplification. To be able to understand that effect, what we did is basically like we perform one-dimensional site response analysis, and we try to compare that with our basically code provisions. Here is the amplification spectrum compared with a Turkish earthquake code, which is almost identical with NIHRB, very similar with Eurocode. So you see that the amplifications for this event exceeds at certain periods our code-based provision. So that is a lesson, or that's an important topic that we need to be careful about. Plus, I would like to say one more thing about basically one-dimensional side effects. These were the results of one-dimensional assessments. So to understand the phenomena better, we perform 2D analysis to be able to model the basin effects. And what we saw that the basin effects not only amplify long period energy, but also they prolong the duration of shaking. So this is a comparison of basically the duration predictions at certain locations in the basin. And so that amplified and prolonged motion was one of the reasons of damage. Definitely there are structural factors which will be discussed later. But before that, before we conclude, last couple of slides, we have not stopped there. We said, as you all recall, that this is not a design basis event. This is more of a 72-year return period event. So what if we had a design basis event? And what will happen in Bayraklı? I would like to ask Professor Altun to simply tell us what is expected to happen after a design basis scenario event. Professor Altun.
Thank you. We know that Izmir is a city located in western Turkey, more specifically in the east of the Izmir Gulf and on the Bornova Plain, which is the graben part of the horst and graben structures. It was formed from the block bounded by the deep slip normal faults trending to east-west direction, namely Izmir fault and Karşıyaka fault, south part, north part, sorry. And these structures are typical for the Western Anatolia conditions. And we try to establish an earthquake scenario if the earthquake will happen in this faults. So this is a near fault to Izmir because the scenario earthquake will be give us some comparing the basin effects, some amplification results. And in that context, we try to obtain many synthetic motions and scale them depending on the fault conditions, rupture conditions in the Izmir fault. And this variation gives us this basin effects and this high depth basin characteristics, amplifications, and comparing the real earthquakes. And this scenario, earthquake scenario studies will be done nearly. And of course, very important for this, especially Bayraklı regions and Bornova regions.
Thank you, Professor Altun. This exercise has shown that if we have a design basis event due to site amplifications and side effects, it is very likely that in Bayraklı region, we will exceed the design basis spectrum, which requires further attention. It looks like we use 1 minute extra time, but we follow the time very carefully. I would like to thank to all of the contributors. Thanks for sharing your enthusiasm and your contributions.
We are slightly over time, but we have one question from the audience and one more that just came up. Nikos Theodoulidis from Ilgac is asking if, based on the damage in Izmir, can we safely conclude that proximity of building natural period with a basins 1D or 2D ones is a reliable proxy for expected damage? This is, of course, a very classical question. I would like maybe to ask Kemal to elaborate and answer.
Thank you so much. Basically, yes, basin effects. If we go back to our slide very quickly, I know our time is limited, but what I will do is I will immediately open that slide to show you the basin. Bayraklı is a very special region. In that region, we have a basin which is basically like extending in the north-south and east-west directions. So that basin is basically making things too complicated, not only in one direction, but in multiple directions. Now you can see this slide. Let me show that topography very well. Yes, this one. See that this is where Izmir Bay is. I assume you can all see this slide. And then when you go in the east-west direction, when you go to east, basically like the basin gets deeper. And this is where the most of the damage was located. If you go to the north or south, also it is basically a pot. So if we have a double basin effect, both extending in the north-south and east-west direction, that is why we need to perform 2D or 3D analysis to be able to understand the basin effects. So bottom line, yes, basin effects are pronounced in this region. No available basin models does not capture the response very well, because here the amplifications are more of a 200% range rather than 30-35% range predicted by available basin models. This is as short as I can respond to the question.
Thanks, Kemal. One more question. I know we're slightly over time, but there are some interesting ones by Aniket Desai. The question is whether or not this behavior and those observations can be extrapolated to other areas and countries, such as India, where Indian and Eurasian plates and some other geographic locations. Can you provide a few comments, please?
George, it's a wonderful question. Philosophically, I am a non-believer in nationality of soil responses. Every soil behavior, every setting, geological setting could be different, but soils don't have a nationality, or mechanism don't have a nationality. So my response to the question is rather simple. If the geological setting and topography and fault systems are comparable, yes, definitely it can be extended to understand a phenomena in India. And by the way, a confession, this is how we learn. Earthquake engineers, we observe what happens somewhere and we try to mimic that and apply it in another place. But when we're doing that, we have to be very careful because sometimes the settings may not be identical.
Thank you, Kemal. And to conclude the session, a very successful one, I would like to thank all 20 or so co-authors, because what you saw is due to the efforts of more than 20 people, much more than those that had the chance to make a presentation. But we also like to thank the 6 speakers particularly.